Hey everyone, welcome back to our next lesson on potential energy diagrams, where we're going to be visualizing the potential energy that's involved in a reaction. We're going to take a look at a couple of different types, both endothermic and exothermic reactions. You're going to learn how to draw and label a potential energy diagram, all the specific components of that. And we're going to learn how to use Table I in conjunction with stoichiometry to be able to write and solve reactions. So to start off here, to kind of help with this idea of a potential energy diagram, which we've seen before, we looked at these at the start of the year real simply. But to kind of move this a little step forward, we want to try and take a look at the diagram here, where we have a guy trying to push a boulder from point A to point B. So he's got to get it up the hill there, down the hill, hit the rock at point B, and cause that rock to move. So we have a little situation here, and we want to consider a couple questions, which I'd like you guys to pause the video after we go through one of these questions, try and answer it, and then check your answer with the explanation that I'll provide. So first question, what must the man do if he wants the rock at point A to collide with the rock at point B? Take a second, pause your video, and answer the question. Well, in order to have rock A collide with rock B, we have to get over this little hill that's right in front of us here. That's the first thing we got to do. We have to push the rock up the hill in order to get it over that hump, and we know that it's going to roll down the hill due to gravity and hit rock B. So he's going to have to provide some type of energy to push the rock up and over there. Question 2. Which line represents the difference in height between the moving rock's starting point and its ending point? Explain. So the moving rock is at point A here. The difference in height between the starting point and its ending point would be this line labeled number 1. If this is the start and this is the end point, the difference there is number 1. Now at some point, if we know what we know about potential energy, this rock at point A has some type of potential energy because it is higher up off the ground than the rock at point B. Which means the rock at point B also has some type of potential energy. So the difference there, point or line 1 here, the change there is the change in height of the rock from start to finish. It's also a change in potential energy that the rock loses from A to B. Question 3. Which line represents the height he would have to climb if he decided to bring the rock back from point B to where he started? So we're going to flip this. So we're going to assume that the guy's going to start here at B. And he's not going to start here, but he's going to end at point A. Which line would he have to climb to bring the rock back to A? 3 represents the line that this guy's going to have to push the rock up to get up to the top of the hill here. And at this point, gravity will take care of the rest and bring the rock back down to point A. Question 4. Which part of the diagram must he always reach before he can let the rock roll? That point is right here. It's the highest point, or it would be the point where the rock has the greatest potential energy due to its position off the ground. So this guy, in order to get the rock from A to B or B to A, always has to get above the top of that hill there, the highest point, and then the rock kind of just, due to gravity, finishes the rest. Rolls down the hill this way if we're going forward. If we're going backwards, it's coming back down the hill this way to its starting or ending points. Throughout this whole thing, the rock experiences a change in potential energy depending where it started, sometimes gaining it to a higher level, sometimes losing it to a lower level, all depending on the direction that this guy is moving the boulder. So I want to keep this in mind as we move through the presentation today. So using PEDs, which are potential energy diagrams, we use these when we want to analyze changes in the energy potential of reactants and products. Think of something like that has a lot of potential energy, like gasoline, which requires oxygen in order to react. A lot of potential in there, a lot of heat that can be released through a combustion reaction, and that reaction produces products like CO2 and water. The carbon dioxide and water products have a different potential than the gasoline and oxygen that initially went into the reaction. We can monitor this and look at the changes using a potential energy diagram. Now, enthalpy is the amount of potential energy of a substance. We call this heat. And I like to think of the H in enthalpy to remind me that enthalpy has to do with heat or potential energy of a substance. And we use the symbol H to represent that enthalpy, and we'll be referring to a lot what we call, and we've seen this before, delta H, or the change in H, or the change in enthalpy, or the change in heat that occurs during a reaction. So H sub A refers to the amount of potential energy or enthalpy of reactant A. And we can do the same thing for B. You can talk about the heat of B or the heat of C or the heat of the reaction, total or delta H. Now we want to keep in mind here that we have a conservation of energy in all of our chemical reactions. So the energy that we start with has to equal the energy that we end with. Now endothermic reactions absorb energy. Remember, N meaning enter. Energy is entering the equation. It's coming into the system. It's being absorbed by our reactants. So heat energy gets absorbed by reactants. Reaction occurs. That heat gets absorbed from the environment, which causes the temperature of the surroundings to go down as the surrounding environment provides the necessary heat energy in order for the reaction to happen. Now, since we added energy into our reactants, the products are going to have more energy than the reactants since they absorbed energy during the reaction. And that extra energy gets stored in the chemical bonds of the product. It doesn't just disappear, but it's being stored now in this reaction in the products C and D. And if we have excess energy stored, it makes something unstable. Remember, everything in nature is trying to go to a lower state of energy. So excess energy makes something unstable and highly reactive. Think of TNT. All you got to do is provide a small little spark and you can make something explode. It's highly unstable. Let's look at an example. Remember, we want to think of our law of conservation of energy. So if the heat of A in this reaction, A plus B yields C, this is a synthesis reaction, we have 40 kilojoules as the heat of A, and the heat of B is 20 kilojoules. Then the reactants have a total enthalpy of 60 kilojoules. So if the heat of C is 110, well, this doesn't match the 60 that we started with, so we must have gained some somewhere, probably from the environment. That missing amount is 50 kilojoules, and that has to be absorbed by the reactants in order to equal out the 110 on the other side. So we rewrite the equation to show that addition of heat as a reactant to give us product C. Now if we double check again, we have 40, 20 plus 50 gives us our total of 110, and our law of conservation of energy is satisfied. Now looking at endothermic reactions, this is using table I in your reference tables. Again, looking at a synthesis reaction between nitrogen and oxygen to yield nitrogen monoxide. Now this reaction here gives us, and if you look in the bottom of your table, it says a minus sign. Remember, a minus sign indicates an exothermic reaction. So a positive sign here would indicate endothermic reaction. And this reaction, the amount of heat here that's absorbed, 182.6 kilojoules, is how much is being absorbed by the reaction as it's written. So we're going to have to pay attention to mole ratios here. Now if we rewrite the equation, we would write the heat, like we saw on the previous slide, as a reactant. That amount of heat has to be absorbed by 1 mole of nitrogen and 1 mole of oxygen to yield 2 moles of nitrogen monoxide. So this shows that in order for this reaction to happen, we have to absorb 182.6 kilojoules for every mole of nitrogen and oxygen to form our product, NO. Our product here now has greater energy than it did in the bonds of the nitrogen and oxygen combined. So this product is considered unstable. Endothermic reactions tend to be not as common because it's not in the nature doesn't want to store excess energy. It's trying to move to a state of lower energy, so it's going to tend to prefer exothermic reactions. Now exothermic reactions release energy, so from our reactants to products now contain less energy because energy is released, and therefore we're at a lower energy state, and nature likes to favor those reactions. Heat gets released into the environment, the temperature of the surrounding goes up, products have less energy than the reactants they started with. Think of after you burn the gasoline. Since the products have less energy stored in their chemical bonds, they are more stable. The CO2 and water that comes out of your tailpipe is more stable than the gasoline that went in. Or if you're thinking of burning paper or wood, the ash that's formed is not flammable, which is more stable than the flammable wood or paper that started the reaction, which would have been on fire. So exothermic reactions tend to be preferred or favored. Again, we'll look at the same synthesis reaction between A and B yielding C. The heat of A having 60 kilojoules. Heat of B having 40 kilojoules. Reactants have a total enthalpy of 100 kilojoules. If we have 30 kilojoules tied up in the bonds of C, then the difference there is 70 kilojoules, and that must be written, that must be given off after the reaction, and must be written as a product. So this shows that we have 70 kilojoules being released during the reaction of A and B to yield C. Now we can check, we have 60 kilojoules, 40 kilojoules, we had 30 kilojoules here, that's a total of 100, and our law of conservation of energy is satisfied. Now comparing this with a reaction on table I, minus sign indicating that it is a exothermic reaction, so this reaction is going to release 393.5 kilojoules of heat for every 1 mole of carbon and 1 mole of oxygen that is reacted to yield 1 mole of CO2. We can rewrite our reaction here, putting our heat value as a product because it is an exothermic reaction, and we're going to write the heat value on the product side because it's being released after the reactants react. Now one of the things that we're going to have to be able to do is adjust our amounts or figure out how much heat is going to be released or absorbed if we're not using the reaction as written on table I. Now what if we wanted to make, instead of making 1 mole of CO2 here, what if we wanted to make 2.3 moles of CO2? Well, we know that based on our reaction, 1 mole of CO2 yields us 309.3 or 393.5 kilojoules. What if we had 2.3 moles of CO2? How much heat would that be? And we get this total of 910 kilojoules being released. And that's all the negative sign is going to indicate, is that it is being released, or it's going to be an exothermic reaction, or we're going to write it as a product. That's all the negative or positive sign is telling us in this scenario. So 910 is 2.3 times greater than 393.5. Now we could also look at this in the reverse direction. These reactions can go forwards or backwards. Now the forward reaction in this case is a synthesis reaction, but the reverse is a decomposition reaction, taking CO2 gas, breaking it down into its component elements of carbon and oxygen. And in order to do that, we have to actually add energy. So if a forward reaction is exothermic, the reverse reaction is endothermic, and this is always going to be true. So if we want to decompose 1 mole of CO2, we need to absorb the amount of energy that was released for the synthesis reaction. Remember, we have to conserve energy, and the amounts are going to stay the same. So the forward reaction releases 393.5 kilojoules, and the reverse absorbs 393.5 kilojoules to decompose CO2 back into its elements. So at this point, you should be able to use table I to determine the amount of energy absorbed or released during a chemical reaction. On to the potential energy diagrams. We're going to come back to the guy pushing the rock here over the hill to try and tie all this together. So these PEDs are a graph that's going to show what happens to potential energy in a reaction from start to finish. Now every reaction is going to start with some type of reactants, so the potential energy is going to start at whatever the heat of the reactants are, whatever the potential energy of the reactants are. So that's why I want to think of that guy where he was at point A, about to push a rock up over the short part of the hill. Now activation energy, this is what the energy that's going to be required to add to the reactants to start the reaction. So this is the energy that the guy has to push to get over that initial hump in order to get the rock to go back down the hill on the other side. So this raises the level of potential energy in the reaction to what we call the heat of the activated complex. This is the point at the top of the hill. This is where potential energy is greatest. The rock has the most potential here. It's very temporary. If our aspects of collision theory work at this point at the activated complex, we can have that activated complex break down to form products, which would lower the potential energy to the heat of products level, wherever that may be, whether it's an endothermic or exothermic reaction. If we don't have all the necessary parts of our collision theory, the activated complex would break down and form reactants again. It all depends if we are meeting all those criteria for a successful reaction. So we kind of think about this here. This is point A, where we had the guy with the rock, and this is point B. And this is actually a reverse reaction of what we saw with the guy pushing the rock. But this is what we call here the activated complex. This is the top of the hill. This is the point that we got to get to every time in order for this reaction to happen. In order to get over the hill, the guy to get the rock over the hill, he's got to at least get to this point. Now the heat of our reactants here is at 60 kilojoules. And the heat of our products is up here at 110 kilojoules. And I'm reading that off the side here. So the guy's pushing the rock from a lower position up over the hill to a higher position. So the potential energy here is greater than the potential energy of the reactants. This is an overall gain of energy from 60 to 110 of 50 kilojoules, and that's our heat of reaction. So just by looking at this, we can see, since we're going to a higher energy level from reactants to products, or from A to B, we have to absorb energy. We show that as writing the heat value in our reaction. A plus B plus heat, so this is an endothermic reaction, yields C. C here would be unstable because it's now at a higher energy level than when it started, and that is not favorable. Now the reverse can happen here as well. The guy with the boulder here at B can push it back up this way, And this would require, if we look at this in the reverse, a release of 50 kilojoules as we bring the rock back down to point A. Its potential is at a higher point at B to a lower point at A, and the heat values are just the opposite of the forward reaction. So we would release 50 kilojoules as opposed to gain. These are all the portions of the graph that you're going to need to be able to label your X and Y axes. Reaction coordinate meaning from start to finish, if we read it from left to right, or reverse, if we're going in reverse, right to left. Heat of the activated complex, the top of the hill, heat of the products, and heat of the reactants. Activation energy is how much energy to get from your starting point, in this case at A, up to the top of the hill. And your delta H. These are your 7 requirements: your heat of reaction, the overall change between reactants to products, from where they start to where they end. Now, just by looking at this, this is an endothermic diagram. We have a net increase in potential energy which is absorbed from the surrounding environment. The kinetic energy of the motion of particles in the environment. Everything starts to slow down, decreasing its temperature, and this reaction absorbs heat from the surrounding and has an overall gain of 50 kilojoules. So the products have more energy than the reactants, and this is considered unstable. An exothermic reaction just looks the exact opposite. We have a net decrease in potential energy, which releases into the surrounding environment as kinetic energy and causes all the molecules of the environment to start moving faster, therefore increasing the surrounding temperature of the environment. Our products here have less energy than the reactants and are considered stable. So we have a decrease here, a decrease in potential energy as we go from start to finish. Now, adding a catalyst to the reaction decreases the activation energy by removing one or more steps from the mechanism. So it's going to speed up our reaction by changing the mechanism as opposed to the collisions. Therefore, the heat of the activated complex decreases. So we see a change to our curve is something like that. So now instead of needing 80 kilojoules of activation energy, maybe now we only need 60 kilojoules. Less heat required means that this reaction should happen faster, as more collisions will be satisfied because they're going to require less energy in order to meet that activated complex and form products. Reactions are reversible, as we've been talking about. We've talked prior about synthesis and decomposition reactions being reverse of each other. With enough energy, any reaction can be reversed. If you can go forwards with one, you can always go backwards as long as you're given enough energy. Now, when a reaction is reversed, products become reactants and the reaction coordinate goes from right to left. So we can read these from left to right, or we can read them from right to left. Right to left would be reactants, products, and left to right would be reactants and products. All depends which way we're reading it. And in both cases, our heat of reaction values will reverse. At this point, we should be able to label the 5 key pieces of information on a potential energy diagram. I've given you the reaction coordinate and the potential energy values on the X and Y axes respectively. Number 1, if you want to pause the video and try this and see how you're doing with this, feel free. Number 1 here is the heat of our reactants. 2 here is what we call activation energy. Whoops. For forward reaction. 3 is the heat of products. And 4, the change between products and reactants. This is what we call the delta H, or the heat of reaction. overall, since the products have more energy than the reactants, this would be a positive heat of reaction, or an endothermic reaction. So this would be endothermic. Those are the pieces that you need to be able to label. You should also be able to draw an endothermic and exothermic chemical reaction when given the energy of the reactants. So we have a endothermic reaction on the left here. I'm going to draw an exothermic reaction on the right, and these can kind of just take a general form. They don't have to be exact. Again, feel free to pause the video and try this. I'm going to show an increase here. And we have products here and reactants. To look at the difference between these, this is not my straightest of lines. The difference here between these is our delta H, and in this case this would be a negative delta H, or an exothermic reaction, because our products have lower energy than our reactants. For catalysts, when we want to show the effect of a catalyst on a reaction mechanism or pathway, we show a lower curve for the activation energy. I'm going to try and draw this a little bit more drastic, so we can see that the activation energy changes. Keep doing that. Activation energy changes with the addition of a catalyst. Make sure you guys bring any questions that you have, write them down, try the examples in the video, and come see me with any questions that you have. Have a great day.